this video, we'll cover the kinetic molecular theory of gases and the differences between effusion and diffusion. While the ideal gas law explains how gases behave, it doesn't provide reasons for why gases behave in such a manner. Thus, we introduce the kinetic molecular theory, or the theory of moving gas molecules. The purpose of this theory is to explain why gases behave in the way that they do. The kinetic molecular theory, for it to work, is based on 5 different assumptions which we would apply to an ideal gas. Obviously, these aren't going to be true to gases in the real world, because we are limited by constrictions such as the law of thermodynamics. However, it's still super important that we fully understand the theory, so let's go through each one of these 5 assumptions. The first assumption that we make is that our gas particles are in a constant and random motion. Our particles will move in a straight line until they make contact with something, such as another gas molecule or the wall of a container, and they will then change direction. The second assumption that we make is that the size of a gas molecule is negligible when compared to the space between it and another gas molecule. Because of this, we assume that gas molecules take up no actual volume. And again, this is because if we had a gas, the distance between our two molecules is insanely massive. There's just so much space. And so the actual size of our molecule doesn't matter. The third assumption that we make is that the collisions between our gas particles are perfectly elastic. This pretty much just means if we have two gas molecules and they come into contact with one another, no energy will be lost to the surroundings. All the energy will stay within these two gas molecules. This obviously can't happen because of the first law of thermodynamics saying that some of this energy must be lost to heat with the surroundings, which is why we say that these laws apply to ideal gases, gases which behave ideally. The fourth assumption that we make is that there are no intermolecular forces between our gas molecules. This kind of adds to our first assumption that they are in constant random motion, because two gas molecules, if they were to slightly go past one another, there would be no intermolecular forces, no London dispersion forces, that would attract them towards one another. Those simply wouldn't exist. So that's what it means when we say that no intermolecular forces exist between gas molecules. And the very last assumption we make in our kinetic molecular theory is that the average kinetic energy of a gas is directly proportional to, and only proportional to, the temperature that our gas is at. We'll be dissecting that one more in depth in just a minute. These 5 rules are how gases behave, and so it's super important that you understand all of them. You also have to understand, however, that this is an ideal model of how gases behave. These exact rules only apply to ideal gases. In general, gases will follow them, but the exact rules will only apply to ideal gases. Obviously, gases can't actually follow all of these rules, since half of them break the laws of thermodynamics. When our gases don't follow the rules exactly, we say that they deviate. A larger molecule, lower temperature, or higher pressure will all result in deviations from kinetic molecular theory. Recall that these are the same reasons gases deviate from the ideal gas law. I went into great detail over the reason for deviations in my ideal gas law video, the one right before this, so if you're looking for more information, I recommend checking that one out. Let's further dissect this fifth statement because it's the most complex of them all. To calculate the average kinetic energy of a molecule, we use the equation kinetic energy average equals 1/2 the mass of our particle times the velocity of our molecule squared. As with other equations, you just need to be able to solve for an unknown when presented with all other variables. For example, if you have the kinetic energy of a gas, and you know the mass of your gas molecule, well then you should easily be able to solve for the velocity that that molecule is traveling at. You must also absolutely understand that the only thing that affects our kinetic energy is temperature. If we have two different gases, let's say carbon dioxide gas and water vapor at the same temperature, they are both at 120 degrees Celsius. The average kinetic energy for both of these gases will be the same. Carbon dioxide gas is heavier than water vapor, and you can just find that by going to the periodic table and adding up the masses of its elements. But because the kinetic energy is the same, just because carbon dioxide is heavier, that just means that its particles will be moving slower. And likewise, if water vapor particles are less heavy than carbon dioxide particles, well that just means that their particles have to be moving faster than the carbon dioxide gas, because the kinetic energy must be the same for both. Make sure that you fully understand this concept. How do we display this information? To do this, we use something called a Maxwell-Boltzman distribution. This graph right here displays the Maxwell-Boltzman distribution for the kinetic energy of noble gas molecules at 100 degrees Celsius. So first of all, the important thing we got to take away from this, all of our molecules are at 100 degrees Celsius. Why is that important? At the same temperature, they will all have the same kinetic energy. So if you look down here at our graph, our x-axis is labeled kinetic energy, and our y-axis is labeled the number of molecules. Pretty much how a Maxwell-Boltzman distribution works is that the area under the curve represents our total number of particles. If we selected this point on the x-axis, this random kinetic energy, to find the number of molecules with that kinetic energy, we would just look at the y-axis. At x kinetic energy, we get y number of molecules. To find the number of molecules with this kinetic energy or less, we solve for this area. And that's pretty much how we use a Maxwell-Boltzman distribution. As you can see by this key I've drawn here to the right, our blue line on this curve represents the gas neon. Our red line on this curve represents the gas argon. And our green line on this curve represents the gas krypton. And I hope you realized it by now, I've drawn every single one of them on top of each other. And why have I done that? Because the x-axis is the kinetic energy, and all of our gases are at the same temperature. You really got to be able to make that connection quickly. If our gases are at the same temperature, they're at the same kinetic energy. So for instance, the median kinetic energy for our blue curve is the same as for our green curve is the same as for our red curve. The number of neon particles that have a kinetic energy of at least this x value, so that's solving for this area here, is the exact same as our number of argon and our number of krypton particles that have at least that kinetic energy. And so I really hope that makes sense to you. That's the Maxwell-Boltzman distribution, and it's really important that you know how to use it. Let's do another example using another Maxwell-Boltzman distribution. And this time, as you can see by the x-axis on our graph, we are looking at the Maxwell-Boltzman distribution for speed. On the x-axis, this graph will tell us the speed of our particle, and on the y-axis, the number of relative particles that have this speed. Again, another important connection for you to make is that in this distribution, all of our gases still have the same temperature. I know it's not listed in this graph, but your problem will tell you. All the gases have the same temperature. However, they have different speeds. How is that possible? Well, to answer this, let's just look at our kinetic energy equation. The average kinetic energy equals 1/2 mass of the particle times velocity of the particle squared. And let's specifically focus on oxygen gas and carbon dioxide gas. The average oxygen element has a molar mass of 16 grams. And so let's say if we had 1 mole of oxygen gas, that'd be 16 grams times 2 because we have 2 oxygen atoms, and then we would get 32 grams. What about carbon dioxide? Well, 2 moles of oxygen weighs 32 grams. We just solved for that. And a mole of carbon weighs 12 grams. So that would give us an answer of 44 grams. So as you can see, carbon dioxide gas is clearly going to be heavier than oxygen gas. If the average kinetic energy for both of our molecules has to be the same, but one of them is heavier, then that heavier molecule's velocity must be slower, because otherwise our equation is false. Again, that should make sense because this is just algebra. And that's why, if we reference our graph, oxygen, its median particle speed, which is at that hump, will be 400 meters a second. And for carbon dioxide gas, again, the median particle speed is at that hump. It'll be less, maybe around 330, something like that. And so now that you know this, without doing any calculations whatsoever, which gas will be heavier? Oxygen gas or ammonia gas? Yes, I know you can easily do that in your head if you have the periodic table memorized, but we can also just look at our Maxwell-Boltzman distribution. Remember that our oxygen gas is the blue line, and it has a median molecule speed of around 400 meters a second. Our ammonia is the red line. Its particle speed is a lot quicker, close to around 550 meters per second. And so what does that tell us? Well, if both of these gases still have to have the same average kinetic energy, but our ammonia gas is quicker, then we know that it must have a lighter mass than the oxygen gas. And conversely, if we know that our oxygen gas is a little slower than our ammonia, then we know that it must have a heavier mass. And that's everything you need for interpreting the Maxwell-Boltzman distributions. They're honestly not that hard. The last part of this video will cover the difference between diffusion and effusion. And it's quite simple. Diffusion is the spread of a substance throughout a space, or another substance. As you can see by this image down here, In our first picture, we have a higher concentration of molecules on the left side of the box and a lower concentration on the right side of the box. The molecules will diffuse into the right side of the box, and then in picture 2, you'll see that the sides are now equal. That's diffusion. Effusion is the escape of a substance through a very small hole. So as you can see in the second image here on the right, again, we still have a higher concentration of gas molecules in the top, but instead of being able to diffuse to the bottom, they have to effuse through this very tiny hole. Eventually, of course, this will happen and we'll have an equal number of gas molecules in each side of the box. As the mass of our gas decreases, meaning our molecules get smaller, our rate of diffusion and effusion will increase. This is explained by our previous Maxwell-Boltzman distribution for speed. Remember, lighter gas molecules will move quicker than heavier gas molecules. And so let's say we have a piece of wool containing ammonia gas and carbon dioxide gas. Ammonia gas is a lot lighter than carbon dioxide gas. And so our ammonia particles will be able to diffuse quicker than our carbon dioxide particles will. And so when the particles finally meet in this tunnel, it'll happen somewhere around this location. Not in the middle, because if it was in the middle, both of the molecules would have to be having the same rate of diffusion. And because ammonia is smaller, it diffuses quicker. You just need to be aware of that principle and the rule that as our molecules get lighter, or as they get smaller, they're going to diffuse and effuse quicker. There's also an equation that goes with this known as Graham's law. Graham's law states that the rate of diffusion or effusion of a gas is inversely proportional to the square root of its molar mass. R1 is the rate of effusion for our first gas, M1 is the molar mass of our first gas, R2 is the rate of effusion of our second gas, M2 is the molar mass of our second gas. You might be presented with a question where they give you the effusion rates of one identified and one known gas, and you need to find the molar mass of the unknown gas. Or they might ask you to compare the rates of effusion between gases. In either case, you'll just be using this equation and some algebra. It's important to note that Graham's law is not on your formula chart, so make sure that you know this equation. And with that being said, that's everything you have to know about kinetic molecular theory. If any part of this didn't make sense, I recommend rewatching parts of the video. If it's still not clicking, just take a break and come back later. Thank you for watching.